Hello? Hello? Hello, Rahul sir?
Yes, I'm here.
Yes, sir. We will be starting in a minute. We are just waiting for other press.
Sure.
Good evening. On behalf of ISIEINDIA, I welcome you all to this webinar on the second module of National Master Certification Program. Today for this session on technical introduction on lithium-ion cells and battery pack, we are having Mr. Rahul Bollini. He is an independent R&D consultant for lithium-ion cells for electric vehicles and energy storage systems. He works with clients for across the globe. He is an expert in lithium-ion cell engineering, fabrication, testing, and validation. He is actively working in this field since 7 years and mentoring over the Over to you, Rahul, sir.
Hello everyone. My name is Rahul Bollini. So, Paul, could you run the slides for me? Because I've joined on my cell phone.
Yes, sir. Yes, I would like to introduce Mr. Rahul.
Yeah, tell me.
So, Mr. Rahul, sir, I just want to give an introduction of yours to all the participants.
Sure.
So today we are having with us Mr. Rahul Bollini. He is an independent R&D consultant for lithium-ion cells for electric vehicles and energy storage systems. He works with clients for across the globe. He is an expert in lithium-ion cell engineering, fabrication, testing, and validation. He is actively working in this field since 7 years and mentoring over dozens of companies. Now I would like to request her to take over the session. Over to you, sir.
Okay. Let's get started. My introduction is already given. So today I'm going to talk about cells and battery pack, and then one of the person actually asked me that are you also going to talk about the market? Then I thought, okay, why not? So I've added some slides about the market as well. So this will be helpful for people who are newly venturing into lithium-ion battery industry. So let's get started. So the first slide is what is a lithium-ion cell? So it all comes down to a cell level. Whenever people talk about batteries and lithium-ion batteries and all, it's basically a lot of cells put together. And so let's get started with the cell. So a cell has 4 major components. There is cathode, anode, separator, and electrolyte. And during charging, lithium ions move from cathode to anode and back from anode to cathode during discharge. And lithium-ion batteries are becoming popular, and they have, they are considered better than lead-acid battery, especially in electric mobility and all that, for the reasons that it has higher energy density, both in terms of watt hour per kg and watt hour per liter, which is gravimetric and volumetric energy density. It doesn't have any memory effect. Suppose memory effect actually means that if the last charge and discharge was not really proper, so that effect will not be carried forward, unlike lead-acid batteries. So, and it has a very low self-discharge. So self-discharge basically means that, just imagine you leave your car. The cars have starter batteries of lead-acid batteries. So if you leave your car and go away for a vacation for a long time, and you come back and you see the battery is completely discharged. So that property of the battery is called a self-discharge. So lead-acid batteries are huge. Lithium-ion batteries are, on the other hand, very, very less. It can be as low as 5% per month. So even if you go away for 3 to 6 months of vacation and you come back and see the battery, there will still be some juice in the battery. So let's move on to the next slide. So let's talk about the types of lithium-ion cells. So people talk about there are so many chemistries, and also I have jotted down all the possible chemistries that you will be coming across. So this is literally everything in terms of lithium-ion. You might also hear about lithium sulfur and all that. Those are not lithium-ion batteries. That is technically lithium metal batteries, where lithium metal is used as an anode and cathode is the sulfur. So let's talk about lithium-ion cells only today because that's what we are focusing on. So the first one is LCO, lithium cobalt oxide. So this is the one which was commercialized by Sony in 1990, and even today this is used in our cell phones and tablets and laptops and all the very portable devices. And then coming to NCM or NMC as they call. So these batteries are very popularly used in two-wheelers. Today if you are buying an electric two-wheeler, the chances are that you are looking at I think someone sent a message that we are not able to see the screen. Amol, can you look into that?
Yes, screen is visible.
Someone left a message in the group, no? Like it says, sir, we are not able to see the screen.
I would request you to one thing, rejoin the meeting.
Okay, so I'll continue. So NMC, like I said, if you are buying an electric two-wheeler today, the chances are that you'll be seeing NMC. So NMC is considered to be having high energy density, both again, in terms of weight and volume. So they are very compact and the weight is very less. So they are very popular. So if you look at a scooter like Ather or Ola, they want to put in 3 kWh to 4 kWh of batteries. So that is possible with NMC or NCA, which is the next topic, next type of battery. NCA is something used by Tesla. Mostly Tesla uses it, and other than that, not many companies are looking into that. And Panasonic is the supplier for that. NCA has better energy density than NMC, but again, safety issues and all pop up, especially when it's being dealt in a subtropical country like India, where the temperatures can easily touch 40 degrees or so. So NCA is not considered safe when it touches 45 degrees, and NMC is not considered safe when it touches 55 degrees, and LFP can handle up to 65 degrees. So the fourth type is called LFP, which is popularly companies are looking to adopt LFP in two-wheeler also, but the challenge being that they are heavier and they take up a lot of volumetric space, and for that reason it is very popularly used in that's not a concern in three-wheeler. For three-wheeler, popularly everybody uses LFP batteries. And then there is LMO. LMO is one of the very old technology. If you have heard of Nissan Leaf, one of the earliest electric vehicle ever made. So they used to use LMO, but the challenges with LMO was that they had very short life, and that's why it never really stayed till today. And then there is LNO, which is theoretical, and some companies have actually looked into it, but it never really took off. And then there is LNMO, which is, you might have heard about Exide signing a pact with S-Volt 2 days back. So S-Volt makes LNMO batteries. It's basically NMC kind of batteries, but without cobalt. So they have a higher potential. And LMFP is basically LFP batteries with manganese dopings. So they have similar properties to LFP, and but you get a higher voltage. So we'll get a little bit deeper about voltage and all that in the further slides. So you can go to the next slide. So let's talk about NMC and LFP because that is what is mostly relevant to Indian markets. If you go to a battery pack company in India, the chances are that you will see they are either making a pack out of LFP cells or NMC cells. So today we are going to talk about only them. So NMC, they, like I told, they have they take up less space and all that. But again, when you're trying to fit in more energy in a given space, you're going against the law of electrochemistry. So the battery tends to become unstable. Lower stability. On the other hand, LFP has higher stability because it takes up more space. There's more metal and battery. The weight of the battery and all that. and it gives you wonderful number of cycles as well. But the challenge being that it cannot be used everywhere where the space constraint is there. So that is being used in three-wheeler and buses. Three-wheeler and buses use only LFP, and a car, a passenger is normally looking for higher mileage. They want more and more mileage, so that is not really possible with LFP, with an exception being that Tata Nexon is using LFP. But if Tata Nexon is looking to make another variant with say 450-kilometer range, chances are that they will have to shift to NMC. In two-wheelers, it's all NMCs. You can look at Ola, Ather, TVS, Bajaj, you name it, they all use NMC batteries. Yeah, we can move to the next slide. So let's talk a little bit about understanding C rating. So basically, when you buy a lithium-ion cell, it comes with a standard data sheet. So in the data sheet, you will see that there is something called standard chart, standard discharge conditions. So it is highly advisable to use the cells within the standard mention or around the standard that is mentioned in the data sheet. So let's talk about an example. For example, a 2600 mAh NMC cell rated with 0.2 C standard discharge rating must discharge at around 520 milliamps. So 520 milliamps is nothing but 0.2 into 2600. So that comes down to 520 milliamps. So that is something the continuous discharge should be. But looking at electric vehicles, they tend to have higher, so you will have to look for cells which support higher discharge. So you can look for 0.5 C, and sometimes if you don't really have a choice, it's okay to use a 0.2 C rated cell. This is continuous I'm talking about, but the energy expected, the output energy expected will not be same as mentioned in the data sheet. Say if a 2600 mAh battery at 0.2 C rating, if it's discharged in 5 hours, it would give you 2600 mAh. But if you are discharging within 2 hours, say at 0.5 C rating, then it might be giving 95 to 97% of energy only. And if you are going to discharge within an hour, then you are probably going to get 92 to 95% of energy. So those kind of calculations should also be kept in mind when you are designing a battery pack, or when you're trying to analyze the cells characteristics and all that. We can move to the next slide. So let's talk about energy auditing the application. So this is more relevant when you're making a battery pack. So whenever you set up a battery pack plant, or you already have a battery pack plant, the chances are that a client approaches you and says, make me a 48 volt 26Ah NMC battery pack. But it's really advisable that you actually go see the product, the application where the battery is going to be put, or maybe do some trials. So that is called as energy auditing, because sometimes the application, the OEM, they could be misguided, or they could be, most of the time they don't know much about batteries, and they are just buying batteries from suppliers, and now they are looking for a new supplier for better quality or better price or for various other reasons. So they could be misguided, to crack a deal by the previous battery company. So it is highly advisable you go double check. If you are looking at a two-wheeler application, probably you can ask for the data sheet of the electric motor. In two-wheeler, it could be a PLDC, PMSM motor, and you can ask for the data sheet of the controller, and then try to, and based on that, you will have to look at the cells, and then sizing of the current, continuous current in the BMS and all that. So, and in case of energy storage application, you need to understand the client's realistic backup hours. Suppose they say I want 2 hours of backup, but then again there are energy losses due to the inverter, so you'll have to look at the inverter and study the inverter. What are the efficiency losses in inverter? Say 95%, so 5% of that should be added back in the battery, oversizing the battery and all that. So this is a common tip I give for any beginners who make a battery pack. So let's move to the next slide. So I always say that look into the data sheet. It's all in there. So think of cell data sheet as a textbook guide. it actually talks about a lot of things. Most of the time, people look for standard continuous charge, standard continuous discharge, what is the maximum continuous discharge, what is 3C, the cell is suitable for me, and they go above. But there are so many various other factors. You could also look at what is the storage temperature. So, most of the times, if you look at cells, they say first 3 months you can store up to 45 degrees. Next 3 months you are supposed to store within 35 degrees, and after 6 months you are supposed to maintain a temperature of 25 degrees, which can be challenging considering our most of the geography of India, the room temperatures can be close to 30 degrees Celsius. So there are lot of information, there are safety and a lot of things written in the data sheet. So I highly suggest anybody to study the data sheet as in depth as much as possible. Yeah, so let's go to the next slide. So let's talk about maintaining a healthy SOC range. SOC stands for state of charge. So let me get started with, did you ever wonder why does a lithium-ion cell bulge or swell? It's because of deep discharge. So deep discharge, basically if a battery has reached its limit and you are still discharging, say NMC can discharge up to 2.5 volt also, but generally I don't recommend discharging less than 3 volt or 2.9 volt. If you go further below that, then you are basically taking away the lithium ions which were initially used in the formation of SEI layer. SEI layer is a layer which is formed when a battery is newly made, a cell is newly made. On day one, the cell is being charged for the first time. It is slowly charged for a lot of hours, and this process makes sure that electrolyte and lithium ions and they form a layer on anode. So this layer has to be intact, and this layer also helps in making sure that the electrons don't flow through the anode to cathode, because the job of the electrons is to come out from the battery negative and flow out of the battery. It should not internally flow. So this SEI layer is a very sensitive and a very depth topic to be looked at. So if you don't want to get very depth into it, I highly suggest that you don't discharge the battery too much. Say if you are looking at NMC batteries 2.93 volt, like I say, because even if you look at the discharge curve, after that voltage, there's not much energy left in the battery, and there's no point, and you're simply damaging the battery for say 2 to 3% of extra energy. And when you're trying to discharge further, the lithium ions which were on day one, which were used in the formation of SEI layer, they tend to disintegrate, they tend to come out, and then the SEI layer tends to get broken, and then the cell gets a mechanical disintegration, and the cell can swell and bulge depending on the form factor. If it's a pouch cell, prismatic cell, cylindrical cell. So that is basically a nutshell, that you don't discharge it too much. And when it comes to charging, if you ever look at a battery, say at 95 or 97%, it takes so much of time to get charged. The point being that as the cell's state of charge increases, the cell's internal resistance also increases. So it's not allowing the energy to flow inside. That's why it takes so much time. And this generally happens during the CV mode, which is the second mode of charging a lithium-ion battery. And I highly suggest everybody to use a CCCV charger only whenever you're going to charge a battery, charge a lithium-ion battery. CCCV stands for constant current, constant voltage charger. And a healthy SOC would be that, if you look at the data sheet, most manufacturers specify that a healthy way to use the battery is don't allow the battery to be discharged more than 80%. Say depth of discharge should be 80%. So I believe that if you are able to maintain at 10% lower cutoff and 90% upper cutoff, that way you can actually discharge the battery in a healthy way 80%, and you don't run into troubles of deep discharge, or you don't get into you don't spend a lot of time charging the battery above 90 degrees. And another thing about charging above 90 degrees is, since the resistance is high, batteries get heated up. and all the heat that is generated, that is basically energy that could have been charged in the battery. That's during that phase, charger efficiency drops like anything. So let's go to the next slide. Yeah. So design the battery voltage as per application. So commonly I have seen most of the battery packers. Uh, let's talk about 48 volt and 60 volt because most packers are focusing on two-wheelers. So I'll talk about that today. So if you look at NMC cells, so this is a very big challenge in NMC cells. So NMC cells, if you are buying cells from China, possibility are that you will see they have written 3.7 volt, and if you are buying from Korean or Japanese brand, they say 3.6. So a lot of people question, like, they ask me, Rahul, what is the actual voltage of NMC? I say it's neither 3.6, it's neither 3.7. It's something to do with the form factor. Say pouch would be slightly close to 3.66, and cylindrical would be close to 3.63, those kind of things. So it is highly recommended that you round it off to the lower edge, to 3.6. So suppose you are making a 48 volt battery. So today most of the companies, they round it off to 3.7, and they take 13 cells in series and say, okay, I have achieved 48.1 volt. But actually speaking, it is more towards the 3.6 volt. And if you do the math, 3.6 into 13 is not going to touch 48 volt. And considering the application, the motor or any kind of load, if that's a 48 volt system, then what happens is basically the voltage supplied would be lesser than what is expected. So to balance the power, more amps is drawn from the current, from the battery. So that becomes a challenge for the battery as well. Batteries tend to get heated when higher current is discharged. So this problem could be solved when you are going with just placing one more cell. You can go with 14 cells instead of 13. And same thing in 60 volt application. People say 3.7 into 16 cells is 59.2 volt, which is okay, close to 60 volt. But I say it's not really close to 60 volt. And considering if you are taking 16 cells into 3.6, it is much lower than that. So I highly suggest go with 17 cells and take the calculation of 3.6. And this is something I highly recommend, but most of the companies, they also come back with a statement that it is something, cost sensitive and all. Sometimes, so I understand there's a balance, but I highly recommend that if you're going against the law of batteries, you are going to face problems. You are going to face issues in future. And as batteries get heated up, the life expectancy of the batteries come down, the cycle life comes down. And if the cycle lives are actually down, then chances are that you are getting the battery back to your factory during the warranty period. So the claim rate can also be higher. So these are something, I tell companies, and this is not a very common issue with LFP because people take LFP nominal voltage at 3.2 volt, and 15 cells in series is technically 48 volt, so that's not really a problem in LFP. But NMC, I have seen a lot of companies, especially older companies who are more than 3 years old, they have been facing a lot of issues on the field, and they have to have so many number of recalls and all that. So let's go to the next slide. So let's talk about impedance or IR, which is internal resistance. Do you know why LG cells are so popular, such a popular choice for electric vehicles? If you look at Hyundai Kona, it is LG cell. If you look at Ola, it is LG cell. If you look at Ather, it's LG cell. If you look at TVS, it's LG cell. There's a reason why LG cells are preferred over any other cell manufacturer. So the reason is IR. The cells have lower IR. The chemistry, the cell engineering is done in a way that they have less IR compared to the competitors when you compare with Samsung, Panasonic and any other brands from any other country. So why do we need lower IR? So lower IR means more current can flow. More current can flow means, since we talked about initially 0.2C rating. So if you are demanding more current from the battery, no problem for the battery. So if you, I can give you a rough brief data. If you are buying cells from popular brands from China, the chances are that they will be around 22 milliohms for a 2.6 AH. And if you are buying, say, a LG cell of, okay, if not 2600 mAh, even 3000 mAh, it is close to 13 milliohms. So there's a huge difference. So that is something, IR actually matters. So if the cell IR is more, and if you're trying to discharge or charge the battery at a higher rate, then a lot of heat is generated, and that heat is nothing but energy that is getting wasted. So during charging, the energy is wasted from the charger, and during discharging, the energy is wasted from the battery. So it is always recommended, and to go with cells that have lower IR. And another thing is, as the cells are aging, as the cells become old, the IR value of the cell increases. So you have to keep an eye on it. So if in future, if you are using smart BMS, if you are able to monitor the IR level of the cells and all that, so there comes a period, there comes a time when the battery becomes unfit to be used for fast charging, because electric vehicles generally they demand fast charging, and it becomes unfit to be able to discharge high power. For electric vehicles generally demand for high power. So that is exactly when the batteries are no longer deemed fit to be used in electric vehicles, and you'll have to, as a manufacturer, you have to recall the battery. Yeah. So let's go to the next slide. So let's talk about the battery pack making process. So first process is basically you take the cells and you put them in this 512 channel. This is just one type of channel. There's 128 channel. There are many types of channels. This is for cylindrical. For prismatic, you get 16 channels, 32 channels, 8 channel, so on. So the idea, the process is same regardless of prismatic or cylindrical. So basically, you take the cells and you charge them completely, so that, because cells come at a different SOC, and you really have no idea how much energy is there. So the best way to know the energy is understanding its discharge capacity. So to know the discharge capacity fully, we need to charge the battery fully. So cells are charged 100%, and then you discharge them to 0. And when you get the data that, okay, so and so cell has so and so capacity, you're supposed to group them. And once you group them, then we go to the next slide. Yeah, we'll talk about it. Can you go to the next slide? Once you group them, then you put them in cell sorting machine. This sorting machine, basically, this one is 11 channel sorting machine, where you are programming OCV and IR. OCV is open circuit voltage. So you'll be programming the values, and depending on the combination of the OCV and IR, the cells will be coming out a channel. So first you group them according to the capacity, and then again you put them group by group in this, and then again you get further lot of groups. In this case 10 groups, and 11th group would be dead cell or unfit cell. So unfit cells are generally less than 1%, so nothing to worry about. So once the cells come out, so all the cells from each channel are taken, and then it is going for welding. So can you go to the next slide? Yeah, so this is a manual spot welding machine. There is automatic as well, single-sided, double-sided, so many. But for starters, I highly recommend that to understand the process, you can go with this. It's economical and it's more flexible. Only thing is it takes time. So companies who are looking to make, say, 30-40 packs per day, this kind of equipment is okay. Yeah. So you take the cells that come out of the channel, sorting machine channel, and then you put them in series and parallel, and you basically put some nickel strips on it. So in this case I'm talking about cylindrical cells. For prismatic cells, basically it will be a screw type kind of thing, M4, M8 screw, and you put a bus bar. So after the OCV-IR, and there's a manual machine for OCV-IR for prismatic after the charging is done. So there's no automatic cell sorting machine like cylindrical for prismatic. And once you put the bus bar and all that, in this case you put the nickel tabbing and put the series and parallel connection, and then we go to the next step. Yeah. Then on the other hand, parallelly, you are supposed to have a BMS tester. So BMS tester, basically you connect a BMS. It has almost characteristics to tell you about the BMS characteristics of more than 30, about 35 types of characteristics. So, which actually pertains to voltage, current, temperature, short circuit of the battery management system, and this is a time-taking process, and hence there are two methods. One is short time and the long time. Long time takes more than an hour, so that is generally done whenever you switch changing a vendor. Short time is more like, okay, is it a pass or is it a fail? So that is how you just connect the BMS and it does it like in minutes, 5 to 10 minutes, the short time thing. And then you connect the BMS to the pack, welded pack. So let's move on to the next slide. So this is a pack arrangement where there's BMS, there is cells, and cells are basically put in a cell holder before putting a nickel tab, so that there is mechanical stability, so that there is not much movement, and there is a proper arrangement and all that. So they are made into a soft pack first, then they are put in a battery aging machine, and then it is finally put in the metallic box. Most of the times people are using MS mild steel metallic box for outer case, and then there is cables and connectors and all that. So let's go to the next slide. So this is the battery pack aging machine. So as a soft pack, before putting the metallic case, the batteries are connected here, and again they undergo similar process like the cells, where you charge the battery to 100 and then discharge to 0, and then charge it say 50, 60, 70% depending on your customer's requirement. Suppose your customer says, I want the battery to be 60% charged, so you will charge it to 60% before dispatch. So this is the basic battery packing process. Yeah, let's move on to the next slide. So let's talk a little bit about the battery pack series arrangement. So when you are connecting plus with minus and so on continuously, so it's a series arrangement. In this case, the voltage of the cells they increase. So a small illustration is given here where 3400 mAh cell is placed. Four of them are placed in series. So the voltage gets multiplied. So the overall voltage would be 14.4 and the capacity would be still intact as 3.4. So this is a series arrangement, and let's move on to the next slide where we talk about parallel. So paralleling is basically done to increase the capacity of the battery, and with increased capacity you can also give an increased rate of current. So in this case it will be basically connected plus to plus and minus to minus and so on. So basically here the capacity multiplies. If you see 4 cells of 3400 mAh all connected in parallel, the overall system would still be 3.6 volt but 13,600 mAh. So this is generally planned according to the range expectancy of an electric vehicle or the backup power expected for an energy storage system, etc. So let's move on to the next slide. So like I was telling earlier that because of increasing IR, the batteries become unfit at some point. So these battery packs have to be recalled. So the batteries with aging and cycling after a few hundreds of cycles in case of NMC, in case of LFP, few thousand cycles, the IR value increases and the retention capacity. The battery has degraded, its retention capacity to hold energy has reduced. And at the same time the IR is also increasing. So there comes a time, if you look at Tesla cars, they say 70% of the energy left, 70% of the retention capacity left. Okay, let's call this as unfit. So there's another reason that as the IR value becomes too high and heat is being generated too much, so this is not really a good environment for the batteries to be placed in, and that is why the batteries have to be recalled But recall does not mean that you're going to just bring it and put it into recycling. Obviously, the batteries are functional; they can be used further, but not for electric vehicles. It can be used for something else. So let's go to the next slide where we talk about that. So what do we do with them? So if the pack is, if all the cells in the pack, if you are able to individually test it and see that they are all good and having the same kind of uniform thing, then you can actually reuse it as a pack. But most of the times, due to the cells placement, the characterization of the cells, the way they experience heat, because if you look at a cell placed in the extreme corners, they experience heat only from two cells, two neighboring cells. But if you look at a cell placed in the center, they experience heat from four neighboring cells. So the chances of cells placed in the center, they tend to go bad faster than the cells placed at extreme corners. So most of the time you have to dismantle the battery pack into cell level and then again do the same process that you did for a brand new cell. You charge and discharge the cell and then you check the CVIR, grade them and then use them for a battery pack where fast charging is not really required. Say energy storage, say solar storage. If you look at solar arcs, most of the places it is 9:30 to 2:30 or 9 to 3 p.m. 5 to 6 hours. So 5 to 6 hours charging is a good time for this kind of batteries. But definitely not this will not go back for electric vehicles, because if you look at electric vehicles, people want fast charging. They want 80% in 30 minutes or 80% in 60 minutes. These batteries are definitely unfit for that. So that is something which can be done rather than just discarding the batteries, because the batteries are still working but not working as an EV grade battery. Yeah. So let's move on to the next slide. So this is basically McKinsey & Company. They just made a graphical model of second life batteries, where new battery packs are made. They are put in electric vehicle, and then used battery pack comes and to a place workshop where repurposing can be done. And if the battery cannot be repurposed, say some cells are almost going to be dead or the IR level is too high to be used for solar system also, then they are sent for recycling. And if they are okay up to the mark, you send them for second life. And then second life is basically mostly energy storage, like I told, for solar application and whatnot. And once the batteries are done there, most of the time the batteries die there. But and then after that the batteries come back to the recycling plant, and then recycling basically happens in two ways. So one is a mechanical disintegration, where you put all the batteries in a shredder, and the shredder would separate all the metals, and there's aluminium, then there is stainless steel, then there is copper, and then there is black mass. Black mass is something of a lot of value. So as of today, in companies in India, they are looking at exporting it to Korea, Japan, China, and there they have the second type of recycling plants, where it is a metallurgical refining process. It could be pyro, it could be hydrometallurgical. So they basically extract the metals. There is lithium, there is nickel, there is cobalt, and then there is manganese. So those kind of thing. And so this is mostly done for NMC batteries, because the value of the amount of lithium in that is high, as much as 7%, as compared to lithium iron phosphate LFP batteries, where it is not more than 3%. And then there is lots of nickel in it, considering nickel prices have gone up in the last week, and cobalt is already super expensive, and manganese is not of much value, but still there is some value, better than iron. So this is the whole chain of second life batteries. Yeah, so we can go to the next slide. So this is something from 2012, I suppose. Yeah, so Chevrolet Volt. This was a very popular hybrid car in the US. So I remember seeing them a lot on the roads of US, and at some point when the batteries were deemed unfit, Chevrolet came up with a good display idea that they will make battery packs out of it and power some commercial spaces. So you can look at this car on the right side, and on the left side you can see there's a energy storage system battery, powered by Chevrolet Volt batteries. So that is the second life, probably charged by solar or slow charging by grid. It could be hybrid as well. So this is an example of it. Yeah. You can go to the next slide. So this is battery recycling, like I told earlier. There's a chain, there's manufacturing, then there is used in application, then it comes back, and then you see if it's fit, you send it for second life. If it's unfit, you put it in the recycling plant, and then the second life batteries at some point come back to recycling, and then metals are extracted and sent back to the manufacturer of cell, and then this is the whole process chain explained here. And the whole idea is that if you look at cobalt, it is produced only in Congo, Africa. So if someone wants to actually manufacture lithium-ion cells in future, say NMC batteries, they cannot go to Congo all the time to buy metals, metal salts and all that. So the idea is, if we are able to create a circular economy within India, so after manufacturing, after a cycle of manufacturing is done, then the metals can be actually procured from the local recycling plant. So that's the idea of recycling, and it's being done in a big way, but it's getting started. It's going to be very big in the next decade. So that is definitely happening. We can go to the next slide. So let's talk a little bit about BMS. What is a BMS? So BMS is basically a battery management system. It makes sure that the battery is operating in its safe zone and controlling the environment, and it is balancing the lithium-ion cells inside the battery pack. And if you look at, again, there are additional features as well in a smart BMS. You can actually monitor the data, store the data, transmit the data via IoT and all that. So on the right you can see a basic hardware BMS. Let's go to the next slide where we talk a little bit about the types of BMS. So there is hardware BMS, which does the basic protection job. So basic protection is basically 5 factors. There is upper cutoff voltage, lower cutoff voltage, then there is continuous current, there is continuous discharge current, and then there is OCD, which is the overcurrent detection, and then there is the temperature sensing. So these are the 5 safety parameters expected in any BMS, and that is something you get in both hardware and software BMS. And in software, like I told, additionally you can expect things such as you can monitor the data, store the data in memory, onboard memory is possible, and then you can transmit it via Bluetooth, CAN, then RS485 is possible, and then IoT, again, cloud storage. A lot of things are possible. So today most of the companies in India are using hardware BMS because it fits in the price range, and today the companies are not well equipped with software analytics. Even if they're able to get the data, they don't know what to do with the data, how to make use of the data. So that is some challenges they're facing. So today everybody is focusing mostly on hardware BMS. So let's move on to the next slide. So functions of BMS, like I told, there are 5, and then here are some additional. If you look at smart BMS, it can actually tell you what is the reading of how much SOC is there. That can be done with hardware BMS as well, where you can just put a OCV, SOC meter, which will based on the OCV reading, it can tell you what is the SOC, but most of the times it is not very accurate. And that is one of the reasons why you see a power bank with a SOC meter or any kind of device, a very simple hardware device with which says a reading, okay, this is the battery percentage, suddenly the battery dies. Because most of the time it can be inaccurate because it's a very simple methodology they use. And there are other things called state of power, which indicates the time of power. It will be available for backup, and number of charge, discharge cycle, total energy delivered since first use, total operating time since first use, energy delivered since last charge, and so on. So these are the functions of BMS. But like I told, the 5 functions are given only in hardware, and software will have the 5 and this additional things. Let's move on to the next slide. So let's talk a little bit about balancing. So this is some challenge that everybody faces as a new battery pack manufacturer. So regardless of they follow all the procedures. Sometimes people call me, they are like, the batteries are not balancing. And this is a very common issue with the LFP batteries. LFP batteries, they tend to have balancing issues with slight aging, not aging after too long. Say after a few hundred cycle itself, you will see, considering LFP has a life of 1500 to 2000 plus cycles, just after 100 or 200 cycles, a lot of balancing issue comes. So the challenge being that, like I told, cells being placed, the placement of the cells and the kind of heat, the environment that it experiences. So that affects the life of the battery, the degradation pattern of the battery, and once the degradation pattern of the batteries become ununiform, then you see balancing issues. And that is the job of a BMS, that if the cells are not balanced, it will basically balance. So the BMS has resistors which will discharge the higher charged batteries to match the lower charged batteries. So today everybody is using passive balancing, where you can expect battery to be balanced with the lowest energy possibility. And here in the diagram, what you see is the active balancing. The mechanism of that BMS is very expensive. It is not really commercialized. Very few companies are making in the world. It can be super expensive. So research is going on for that to make it more affordable. So active balancing, basically it will make sure that the higher battery and the lower battery, they meet up somewhere in the middle. The cells meet up, the energy content, the SOC range comes to somewhere in the middle, where they are all equal, rather than the highest coming down all the way to the lowest to match. Yeah, so let's go down, let's go to the next slide. So let's talk about business opportunity. Like I told in the starting, one of the participants actually asked me, are you going to talk about market as well? I told, okay, why not? Let me just add a little bit about it. So basically, there are two types of things. You can either manufacture cells. The capex is going to be huge. I mean, really huge. And I'm a consultant for that, so I can tell you for sure. And then there's an opportunity to make a battery pack. So if you are, other than making battery packs, these are the components that go inside battery pack. There is cells, there is cell holder, nickel tabs, cables, connectors, BMS, and then there is FRP sheet, there is EVA foam, battery case, shrink wrap, and barley paper. So these are something which are used in most of the battery packs. So manufacturing of this or trading of this is also going to be a big opportunity, not just manufacturing cells or trading cells, not just making packs. These are also some materials that obviously packers are going to need. So I just gave a basic overview about that. You can move on to the next slide. Yeah. So if you are making if you are making battery packs, so here are some applications. I thought I will let you know. You can choose whatever you want. So if it comes to electric vehicles, there's two-wheeler, there's three-wheeler, there's four-wheeler, buses, commercial vehicles, etc. Commercial vehicles has not really taken off, but in the years to come, it's definitely going to take off. And then there is energy storage systems such as telecom, UPS, for that is basically home UPS or commercial UPS. Then there is diesel generator replacement battery, solar energy storage, etc. And then when it comes to portable electronics, there's power bank, medical devices, laptop batteries, etc. So these are some industries, some applications that you can focus as a battery packer. Yeah. Next. So battery reusing and recycling, this is also an opportunity, upcoming opportunity, because considering the market is growing very fast, and the industry, technically I would say, I've been observing from last 4 years, it is actually growing very fast, and most batteries don't come with more than 3 years warranty. So already there is a lot of reuse and the recycling market available right away. So people are looking at it, and at least I would say in the next 3 to 4 years, it's going to be much more than that. So this is also where, like I told, the process, you can either procure it from OEM batteries and dismantle and reuse the cells, or you can buy completely dead cells from battery packers or companies who are reusing and all that, and put it in a shredder, like I told, the mechanical separation process. And if you have volumes, you can go for the metallurgical refining process as well. So these are some battery reusing and recycling opportunities. Yeah. So that will be all. So I generally say in the end that batteries are dangerous goods. Please handle it with care. There's a reason why it's listed as dangerous goods. They can catch fire. So we have to be very careful whenever we are dealing with it. Whatever help is required, always take help from an expert. So that will be all. Any questions? I can take them right now.
So there is one question in chat box.
Yeah, I see one question about BYD blade batteries. Let me just read it out. It says, how about the brand BYD use blade battery? Something has the range. See, batteries don't specify how much range is given. It's the capacity of the batteries that decide how much range comes out. And blade batteries are nothing but a prismatic battery in a different shape. And they're called as blade because of the long structure. I've written an article about it. You can just, record, I'll just share it. Yeah. So there you will get.
Sir, actually, I am not able to write any messages in the chat box.
You can directly ask one of the.
Yeah, sure. You can put the question.
Hello.
Definitely, EVs are going to be the future of automobile. Definitely, but I wouldn't say that it will completely replace. The growth rate is going to be high, and it is not really predictable by when they would completely overtake the market. Because see, selling EVs is different thing, and on the road, there are petrol vehicles already on the street. They also have to be taken care of. Petrol stations are not going to disappear anytime soon. Considering someone who purchased a car just today, for next 15 years, they'll be given the support because they have paid the lifetime tax. So petrol pumps cannot disappear for the next 15 years. That would be injustice done to them. Yeah. So we know that sodium. Okay, Reliance acquired Faradian. The chemistries I have already mentioned, the types of lithium-ion batteries. So sodium-ion again, if you are looking at LFP battery, it is basically lithium iron phosphate. So sodium basically replaces lithium. It becomes sodium iron phosphate. And if you look at NMC battery, that is nothing but lithium, nickel, manganese, cobalt oxide. So basically, sodium replaces the lithium component over there. As of today, it is not commercially available. So people can talk all day, there's so many things people will talk, but let's talk about today what is there. It will come in future, hard to predict, maybe 2 years, maybe 5 years. And then again, sourcing the raw materials and the economies of scale has to support to be able to match the price. As of today, if someone wants to make sodium-ion batteries, it's going to be expensive than lithium-ion batteries. That much I can tell. Because the world has an installed capacity of more than 500 gigawatt hour, and sodium is not even 0.5 gigawatt hour. So 1000x, there is going to be a difference in the raw material sourcing and all that. So as of today, that is not good. going to take off very soon. And sodium ion, if you look at the energy density, it's not very good at the mark. It's not up to the mark. So even if you look at Reliance has no business in energy in electric vehicles. That is solely being done for their. They have a lot of telecom batteries, and for the energy storage market only. So they can target LFP batteries and replace it with sodium ion batteries. And someone asked which brand of battery is the best. See, that's a very vague question, to be honest. Best is LG, but also the most expensive. So I tell people, you get what you pay. You pay good, you get good. So if you want to go with LG, no doubt. Yeah, then alternative fuel introduced in future. Alternative fuel, hydrogen fuel cell, that technology is also being worked. But for a country like India, where green hydrogen possibilities to take off will be much challenging, because firstly, our grid is powered by coal. So the world is looking at green hydrogen only, and green hydrogen comes with solar powered electrolyzer, which would split the 9 liters of water to generate 1 kg of hydrogen. So those kind of challenges. Again, water is not available everywhere. So there are challenges, and if you're talking tons of hydrogen being generated, then we are talking kilotons of water. So that kind of challenges are there. But yes, it is coming. Lead acid battery, I always tell people, it is a market which is never going to die. It is always going to be there. Maybe it's market share will reduce, but the price that it's being sold, no battery can ever match that. And lead acid batteries are not bad. It's just that in electric vehicles they become too heavy. They take up a lot of space. But for energy storage, even if you look at anybody's home today, in fact, there is not any companies who are selling home UPS batteries using one battery. So home-based batteries, UPS batteries, and all are dominated with lead acid battery. And not to forget about starter batteries. Starter batteries are basically in your car and two-wheeler. That is going to be there. Lead acid is going to be there for a long time, because that's a price-sensitive market. How can we avoid the swelling of battery? Yeah, don't deep discharge. If you are looking at an NMC battery, don't discharge lower than 2.9 volt or max 2.8. Don't go below that. Can you elaborate about dynamic balancing? I'm not sure I spoke about any dynamic balancing. There is active and passive balancing. So active, like I told, it's not really there in the market. And passive is something which you get today. So passive balancing.
The question is being put by me. Thanks, Rahul, for putting the things so effectively in such a shorter time. I was asking about active balancing. If the dead cell is going to happen over there in the battery, so BMS will recognize and separate it out. But is there any way, if my demand is going high, and that very time I do have a fixed configuration of the set of cells, so it can be changed from series to parallel, and my charge balance equation remains constant, or I can meet up to the demand what I am expecting as a vehicle build.
Yeah, I have heard a company doing like that. I'm not sure if you're associated with them or not, but yeah, a dynamic kind of thing. That's not really a balancing thing. That's more of like a where the way the cells are connected, you can actually change them. Where the voltage, say you are connecting 4 cells in series, 4 cells in parallel. So whenever you want, you can actually bring down all the cells to 12 volt, or if you want, you can take it to 48 volts also. So that is something I think you're talking about, but that's not really there in the market. Maybe some startup is working. I saw one of the proposals with one of my clients. That's not really taken off in the market. But yes, that's a good product. But if you look at products, the voltage is always fixed, and you cannot power a battery application with lower voltage. So the dynamic that you are talking about is basically, where you can actually convert higher voltage to lower voltage with higher capacity. And again, the BMS change has to be done. So the BMS is what you are asking, right? The supporting, it will not support, because BMS,
What I was
the cabling,
what I was
BMS,
asking.
if you're if you're looking at the way BMS is connected to batteries, they're all connected in series connect. So if you're actually changing, if you're adding more series connection, again, those cables have to be added.
Nee, that's what I was just going to ask. The IR over there, you are looking for a part which is being driven up to the battery which is coming to. So you are considering all the in-between paths also, correct? So in that case, how you differentiate that it is the IR which is getting raised inside the battery or outside the battery? How you differentiate? First,
inside battery is taken, outside and all, you have to change the cables and all that. You change the cables.
Mechanism. In order to figure it out,
what exactly? IR is taken only at cell level. Once it's made into a pack, nobody even talks about IR. Then it becomes all capacity and voltage only. IR is a property of a cell, inside the cell.
Only
and if you are going with, and if you are going with spot welding and all that, if you are using the wrong type of spot welding, and if you are using the wrong type of nickel tap thickness and all that, then you can expect some IR to be grown. So if you are seeing above the tab, if you are looking at the IR again, if you are checking it, and then you will see it will be higher. But generally, how the industry works is they want to understand at the cell level. And once they are all going into the pack, all the same IRs are connected in series. You can always in parallel, you can always use a different IR, that's no problem. But in the same series connection, you are supposed to use the same IR. So that's how it is. And externally and all, that will be there in every system. It's not really in our hands. It depends on the type of cable.
As the nature changes, the IR value also differs. As the aging effect goes, the IR within the battery, the IR pattern also changes.
Yes. The cell itself. Care of the cell will increase.
Okay, understood. And one thing, if the BMS somehow fails, then what is the fallback option?
It will fail. It will fail. BMS will fail, and every electronic is designed to fail because they all have a life. They all have a life. If you look at MOSFET, they have a switch on, switch off times. The number of things. So if you buy a Toshiba, it has about 1,000 switches. If you buy, Infineon, they have 10,000 switches. So you need to understand the BMS also. It's not just that you just buy everything and you make a pack. There are more than 400 companies who do that without knowing anything. And when the batteries are catching fire, then they are realizing something is going wrong. So when BMS fails, there are two options. So I have personally worked on BMS development, I can tell you. So half of the time, or depends on your complete architecture of your BMS. But the possibilities are that either it will give a bypass. Bypass is basically that it will say, I am not involved in this transaction. And if you are actually charging the batteries will overcharge and catch fire. And the second possibility is where it will cut off. The BMS will die, and at the same time it will cut off the connection.
See, that's what we are doing for the conventional. We are doing for the conventional control systems also. As you rightly said, we are cutting it off so that my ECU should not be into the picture.
Correct.
I can say.
So that you can take it to the computer and they will analyze what is the issue and take care.
But we will put the vehicle in the...
It will bypass.
We will put the vehicle. That is what I was just asking. Will we put that thing as a mitigation into the lift-off mode or other modes so that it can support the vehicle in that scenario?
General, nobody is doing it. You can feel free to put all the kinds of electronics. I highly suggest buy BMS from good companies. Don't be price sensitive when it comes to BMS. If you look at all the premium scooter companies, they are investing very heavily. If you look at Bajaj, they pay more than 10,000 for a BMS. But like I said, most of the 400 companies, they don't pay more than 1,350 rupees for BMS. So the risk on the road.
Correct.
It's huge. And that's why batteries are catching fire. It's always the BMS, it's not the batteries. Batteries are naive and they are basically programmed. So you have to take care of them, upper cutoff, lower cutoff, and the amps that has to be discharged, that has to be charged. So many things are there. That's the function of a BMS.
I'll take it as an integrated thing, as a controls.
See, batteries property is fixed. BMS is the dynamic thing which is actually, understanding and communicating, and it's like we call it the heart of the system. And if it feels okay, the temperature of the battery has risen too much, okay, I'll cut off. If too much of current, basically OCD, like I told, over current detection. So if you're using a 50 amps BMS, overcurrent detection, you have put it for 100 amps. So the second it realizes that 100 amps is being pumped out of the battery, it will cut off. So that is all the property of the BMS.
Right. Agreed.
Yeah. I think there was one more question. Let me see. Any book suggestion? I'm not sure. I don't read books and all. Maybe I fall asleep, reading them. So you can. I'm not sure. Books and all. Maybe you can read some of my articles. Like I told, it's very simple. Just make sure you're using the good quality and the good. Like I say, if you're making a small battery pack, most of the people want to cut corners using thinner nickel tabs and all that. If you're cutting corners, then yes, even the book is not going to help you. No book will tell you what is going to be the thickness of the nickel tab. That much I can tell you. They will just tell you the process.
What is the
Unless you go into
which is
field,
the
what is that?
best simulation tool we can use or we can go for?
I don't believe in simulation personally. I believe in putting a data logger and putting in the vehicle and get me the real data. There are so many companies I've seen, they want to simulate and simulate and simulate. Their product will never come out. I like to make a product and put it outside. Simulink, obviously, Simulscape, what else is there? That is what people use. I never touch computer.
We need to have something 3D. Okay.
Yeah,
Understood.
I personally believe make a battery, put it in a real application, put a data logger, or if you have a IoT based, PMS, the data and see how it. Or if you actually have a battery pack charger, discharger, raising machine, which was there in the final process of battery packing, you can actually get your data over there. You can simulate it, using different kinds of C rating, charge ratings, discharge ratings, and all that. All that is possible. And if you want more simulation, actually do temperature simulation, where you will get, the temperature chambers, and you can actually put the battery pack inside and charge them at different C ratings. There are some companies in India doing it as high as 45 degrees Celsius. They put a whole pack in 45 degree chamber and then charge it at 0.5 C, discharge at 1 C rating.
Okay.
Yeah.
Understood.
So there is Vikram who is asking about who are going for lithium-ion cells giga scale. We can see pilot scale R&D, but no news on mass manufacturing. See, this year no factory is coming up in 2022, 2023 also no cell. From 24 onwards, you can see companies who are qualified in PLI, Government of India's PLI, which is production linked incentive. So for 50 gigawatt, they have put a deadline that you have supposed to set up the plant in 24 months from the letter of approval. Letter of approval, I think, is due in June. So 24 months is given, and then after that, they're given 5 years of time to scale up to 5 gigawatt hour, and they should have sold for 5 gigawatt hour, and then they're eligible for 360 crores per gigawatt hour kind of subsidy calculation, which equals to 50 gigawatt hour for 18,100 crores. So that is the plan of Government of India. But on the other hand, there are companies who are like, okay, regardless of the policy, I will go forward. I have my market. So there's one company, they are in Andhra, they are setting up plant for cell phone batteries. Maybe they have a tie-up, maybe they have an order already. So that is one. And then there is one more company who is setting up specifically for buses, because they want to have their own bus manufacturing and all that. So regardless of PLI comes to them or no, obviously they participate in PLI, but regardless of it comes or no, they would be having a plant. And setting up a plant generally takes anywhere up to 15 to 18 months. Giga scale. Megawatt scale, 12 months. I have seen 7 months also in China, possible. Yeah. And so raw material is, if you look at battery pack itself, I showed a list of 11 products. Everything is imported, except cables. People buy polycap cables. Other than that, everything is imported. All the 10 components. Cell holders, everything is imported. Same issue is going to be when people are going to make cells. All the things are going to be imported. It's not like we cannot make it. No manufacturers coming forward to make them. And now finally I have seen there are some companies who are exploring it, who are some chemical background, but even for them to launch a proven market, market grade product, it can be challenging and time consuming. So that kind of issues are always there. Supply chain is one of the reasons why companies don't come forward. They don't want to be the first all first mover advantage is always there, but yeah, that kind of thing is also there. And any other questions I missed? I think that is all. Any other questions? Amol, any other questions? Did I miss anything, or anybody wants to ask anything?
Okay, so there is no more questions, sir. So thank you, sir, for enlightening session and for giving us the brief introduction on technical parameters, applications, design requirements, manufacturing processes, recycling of batteries, EMS, and what are the business opportunities in this sector and other various parameters. So thank you for giving this enlightening session to us. And thank you for your valuable time from your busy schedule. And it was great to hear you, sir, on this topic of batteries and BMs. Thank you.
Okay, thank you everyone.
So I hope all the participants get to know more about the lithium-ion cells and battery pack and the BMS. So this was our second session from the Professional Master Certification Program in AV Engineering. So if you want to learn more about the EV battery pack, powertrain, motor, you can join our Professional Master Certification Program in AV Engineering. The link of the same is given in the chat box. You can put your inquiry. Our executive will contact you for the same. Thank you.
Done? मीटिंग एंड तो करना, ये काम अगर खोल रहा है